Hello friends, this is Dr. G. Srinivasa Gupta from Department of Mechanical Engineering of VJEC JYOTHI, Institute of Engineering Technology. As a part of Dynamics of Machinery course, we are discussing mechanical vibrations. Today we will discuss under mechanical vibrations, lateral vibrations of shafts. As you know that the lateral vibrations are also called transverse vibrations. Transverse vibration analysis of shafts focus on the lateral means sideways. The vibration will occur of rotating or stationary shafts due to mass distribution, also due to some elastic property, and support conditions also leads to this sort of transverse or lateral vibrations. This is a critical for predicting critical speeds. Critical speed is the most important phenomena, which is when a rotating shaft, critical speed is the speed for a rotating shaft. At rotating speed, the frequency, if it matches with the natural frequency of the shaft, then there will be a resonance, lot of vibrations and noise is the phenomenon. Critical speed is the speed of rotational shaft, the rotational frequency at which coincides with the natural frequency of the shaft, then there will be a resonance. We can say it is a large amplitude of vibrations and noise which leads to failure of the shaft. So we need to avoid the shaft running under critical speed. So always it is around 20% either above or below the natural frequency will use to run the shaft. That is rotational speed correspond to that frequency. So transverse vibrations leads to bending of the shaft. Bending obviously occur perpendicular to the axis of shaft. So it undergoes transverse vibrations. So it will occur in all turbines, motors, pumps, okay, wherever transmission shafts are there. So causes of transverse vibrations because of unbalanced masses that leads to eccentricity. So mass located at eccentrically some distance, that means mass center of the all the masses of the carrying elements of the shaft not aligning with the center of rotation of the shaft, then there will be a eccentricity of mass which is rotating, which creates centrifugal forces and misalignment of the shaft with the bearings. And external dynamic loads also causes these transverse vibrations and shaft flexibility also and bearing imperfections. If bearing is not properly aligned with the shaft axis, then there will be a transverse vibrations. These are all causes of transverse vibrations. As just mentioned, critical speed is the speed at which shaft vibration becomes maximum due to resonance. So generally natural frequency, we know that Wn of the shaft we can write G by delta. Okay. So where delta is static deflection due to load, G is acceleration due to gravity. This is valid for lateral vibrations of shafts also, this relation. As we have seen in longitudinal vibrations, similar relation. So for example, a single disc on the shaft, let us say a simple case, a shaft, okay, having mounted on the bearings shaft, okay, supported in between bearings, and a single disc, it is carrying a single disc, pulley, gear or whatever, flywheel, okay, midspan, let us say center. It is like a it behaves like a spring while its rotation. Then static deflection, you know that when this is supported, a simply supported beam, you have studied from fundamentals, if it is carries a load at the center having length L, then beam material property E, Young's modulus E, and moment of inertia of cross section I, then the maximum deflection occur at where load is acting, that is WL cube by 48 EI. You know, it is derived from fundamentals. This is deflection. Then natural frequency, obviously you can calculate root G by delta. Substitute this delta and you can calculate natural frequency of this system. Now critical speed, this with this speed you cannot run the shaft, otherwise it will 60 by 2 pi you can calculate in RPM. In suppose in revolutions per second, then you will have 1 by 2 pi into square root of g by delta, that is omega n by 2 pi, that is speed in RPM. So if you multiply with 60, then you will get RPS. If you multiply with 60, you will get RPM, revolutions per second. That speed should not match with the natural frequency of the shaft, otherwise it will, there will be a phenomenon of resonance. So this is this way you can check this, whether that critical speed, so that means speed due to rotational speed, that is angular velocity, it is having some rotational speed. At that speed, if you find frequency, then that should not coincide with the natural frequency of the shaft. Okay, so you are able to understand this. I think we will go further in details for having more clarity. Suppose in case of multi-disc shaft carrying number of discs, 1, 2, 3, like that, 1, 2, 3. Okay, it is supported in bearing. Let us say it is like a simply supported shaft. In this case, one approach is we can use Dunkerley's method. Dunkerley's method, what it tells is the frequency, the critical speed of the shaft, overall speed with this all these discs, then you can calculate for only disc 1 is there, then what is the speed, and this is 1 by omega square, that is speed, overall speed is 1 by omega 1 square, only disc 1 is attached, then what is the speed of the that is angular velocity of the shaft, the omega is angular velocity, plus 1 by only 2 is there disc 2, then what is the corresponding angular velocity. Similarly, omega 1 by omega 3 square, plus so and so on, as many number of discs as we can write this. So this gives actually this is called Dunkerley's method. This is more conservative and it is lower side value it is going to give, lower side value of critical speed. The W is the speed which we can say critical speed. Okay, we will see all the loads carrying by the shaft should not run this critical speed, means it should not equal to natural frequency of the shaft. This is Dunkerley's method. In Rayleigh's method, we can also write omega square equal to sigma Wi Yi and by algebraic sum of Wi Yi square. Yi is here, it is deflection at each mass, each into I means 1, 2, 3, 4, okay, weight of this each disc and corresponding deflection at the location of the disc by algebraic sum of Wi, weight of corresponding disc, into corresponding deflection square. So this will give omega square. Okay, so this is accurate approach, and okay, this requires to solve this deflection curve equation, and we need to have deflection at each and every disc. Okay, so this is the method. This is called Rayleigh-Ridge method. With this also we can find critical speed. Okay, so whirling of shafts when rotating, the shaft bends due to centrifugal force. Okay, at what happened, critical speed, if shaft runs at critical speed means speed of the shaft, rotational speed, corresponding frequency should not equal to natural frequency of the shaft. Then if it is matching critical speed, means speed, natural frequency of the rotational speed matching with the natural frequency, then the consequence is large amplitude, it will vibrate, and which is known as whirling of the shaft. It may be forward whirl, backward whirl. There are two types. Okay, so now coming to the effect of damping. Damping also, if we use some damping element, okay, damper element, then it reduces amplitude at resonance and does not significantly change critical speed, important for safe operation. So damping element need to be incorporated to avoid this resonance also. So, and there will be some gyroscopic effect also on the shaft. If high speed rotors, shaft is rotating with high speed, then disk rotation produces gyroscopic couple also. So alters natural frequency, it changes natural frequency. So we need to take care. And practical design considerations for the shaft while designing carrying number of discs or rotors, then avoid operating at critical speed, increase stiffness increasing will reduce the speed, reduce mass or eccentricity, and use proper bearings and damping. Bearing alignment and damping element need to be selected properly. Then balance rotating parts. Rotating parts need to be balanced. Balancing, we have seen how to balance various rotating elements and rotating masses. Okay, we need to see that balancing is carried properly. So these are the practical design considerations. One need to take more more way of checking these considerations. Now, so the year so far we have seen natural frequency, we can write square root of G by delta, and delta in case of simply supported beam carrying single disc, then this is W is mass carried, weight carried, WL cube by 48 EI. Dunkerley's method, we have used 1 by omega square equal to 1 by omega I square, algebraic sum of. So that means all the rotors 1 by inversely square of omega, that means angular velocity. So we can find the speed, overall speed of the shaft rotating. Similarly, Rayleigh-Ridge method, we can use this relation. So more flexible shaft, then lower critical speed we have. More mass, higher deflection. If mass weight carried by the shaft or disc, then deflection is very high, then frequency is low. Okay, so because you know that K by M, that is the square root of K by M natural frequency, we can write this, find the natural frequency. In case of particular rotor is mounted, then G by delta we have to verify this omega. Okay, then it should not coincide these two values. Okay, these two. Of course, this also we can write this, in this case this delta is static deflection. But speed rotational, frequency or rotational masses, what is the corresponding deflection? This is the delta. Okay, so stiffer the shaft, higher critical speed. As you know that the stiffer means stiffness coefficient, that is K is more, then higher the speed. Okay, these are all about this. Then coming to any other cases of shaft, this is simply supported shaft carrying central load, we have seen WL cube by 48 EA. Okay, so if you see, suppose a shaft which is a beam or shaft, here shaft also simply supported beam or shaft supporting two bearings, we are saying. Here this is applicable for beams and shafts, because beams are transverse loads, shafts also carrying loads which causes transverse deflection. So this in case of beam, if I take cantilever beam, cantilever beam carrying a simple load at free end, then you know that the deflection maximum occur at free end, you will write WL cube by 3I. Is it or not? Okay, so in this case we can also find omega n, omega of this is G by delta. So if natural frequency should not coincide with this frequency of this load application, otherwise it will be a problem. Understand? Similarly, if it is in the shaft cantilever type and shaft is simply supported, we have seen this, then if you have a simple shaft having load, so then you can have, this is mg, let us say, I will write, so mg into this is L, mg L cube by, you will have this is total length is L, mg L cube by 48 EI we have written. Suppose this shaft is carrying uniformly distributed load, this simply supported shaft. Instead of load is focused at one location, it is uniformly distributed load. Then similarly you can have deflection at the center only, but from mechanics of solids you might have seen the deflection delta maximum occur at center is 5 by 3 5 W. This is load per unit length. W, small w I will write. So this W L power 4 by 384 EI you will get. Okay, you will get this relation. Then use this to find this natural frequency means if you want this one F1, then W by 2 pi into square root of G by delta. Delta substitute this value and check this. The loading frequency. This should not coincide with the natural frequency of the this beam or shaft. Okay, otherwise there will be a resonance. So like that you can take different cases, and suppose simply supported beam having a load which is carrying from one end it is A distance and other end it is B distance. Then you will have corresponding relation in mechanics solids where maximum deflection occur. Maximum deflection occur near the load. It is not exactly at the load in this case. You have corresponding deflection relation you have seen in mechanics of solids. Use that and find the frequency of rotation. Okay, then you can compare with the natural frequency of the material of the shaft. Similarly, whatever condition, loading condition, delta deflection is important to find rotational frequency of the shaft. So this is about critical speed. We are going to discuss in our next session more detailed way of analyzing the critical speed of the shaft. Okay, so this is simple way of analyzing the critical speed of the shaft. Simple concept. More elaborated detailed discussion we will make in our next session, but we will take a simple problem. Let us see. A shaft carries 3 loads, discs, different positions. Static deflection at the disc due to their weight acting individual. So at each weight 3 loads it is carrying 3 discs. Similar one, this one. Okay, as at each 1, 2, 3. Okay, at disc 1 deflection is given 2 mm. Disc 2, 3 mm. Disc 3, 4 mm deflection. Find the critical speed of the shaft using Dunkerley's method. Apply that method. 1 by omega square equal to 1 by omega 1 square. So how do you get omega 1, omega 2, omega 3? 1 by omega square equal to 1 by omega 1 square plus 1 by omega 2 square plus 1 by omega 3 square. 3 discs. So how do you get omega each disc omega? So you consider at a time one disc only. Other discs are not there. Then what is the corresponding omega 1? Similarly consider second disc only. Then calculate omega 2. Similarly consider disc 3 only. Then calculate omega 3. Then you can combine like this using this relation 1 by omega square equal to 1 by omega 1 square. So omega 1 how do you calculate? Delta 1 let us write in terms of meters. 2 mm given 0.002 meters. Similarly delta 2, delta 3. Then take G is 9.81 meter per second square. Then omega 1 is G by square root of G by delta. Use that and you will get in this case 70.03 radians per second. Similarly omega 2, omega 3. Omega 2 is 57.18 radians per second. Omega 3 is 49.52 radians per second. If you apply that 1 by omega square equal to 1 by omega 1 square plus 1 by omega 2 square plus 1 by omega 3 square. That is if you calculate it, you are going to get 0.000918 meters. Okay, this is this value is 1 by omega square. Okay, this value. Then omega is 1 by this one is 1 by omega square. You will have then omega, you calculate omega from this. It is square root of, because 1 by omega square is 0.000918. Then omega square equal to 1 by 0.000918. Omega equal to under square root of 0.000918. So you will get omega. Omega you got 33.0 radians per second, omega. So RPM you want to write, then obviously you can use, okay, omega by 2 pi will give cycles per second, and RPM cycles per minute you want, then that is equal to RPM 60 into omega by 2 pi. So use this and use this omega and calculate n. You are getting here n is 315 RPM. So because of this rotation, the speed of rotation is n is, because of all the disc carrying by the shaft, 315 RPM. So this should not coincide with the natural frequency of the natural frequency you can calculate. Okay, so using this relation K by M. So natural frequency of the shaft should not coincide with the frequency of rotational, okay, speed, that is this omega by 2 pi. So with, there must be some large deviation should be maintained while using the shaft. Okay, this is, with this I am concluding this lecture. Next lecture more detailed elaborate discussion we can make on this topic. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.